Welcome to The Explainer. You ever wonder how your phone instantly recognizes your face? Or how a self-driving car can possibly see the road ahead? Well, today we're going to break that down. We're talking about how a computer goes from just seeing a bunch of pixels to actually recognizing things in the real world. So let's start with a problem that sounds simple, but is actually surprisingly complicated for a machine. Imagine this is your job. Build a machine that can sort fish on a conveyor belt just by looking at them through a camera. For you or me, pretty easy, right? But for a computer, how in the world could it learn to do that? I mean, this is a huge challenge. It requires a totally different way of thinking, a special kind of learning. To really get how a machine tackles a problem like this, we've got to get a handle on a few core ideas first. These are, the building blocks for everything else. Okay, first things first, machine perception. You can basically think of this as giving the computer senses. It's the ability to take in all that raw info from the world, like the image of a fish, and just begin to make sense of it, kind of like how our own eyes and ears work. And that leads us to machine learning itself. Now, this is where the real magic happens. Instead of trying to write a million lines of code to describe every single possible fish out there, we just give the computer a ton of data and let it learn from experience. The whole point is that it gets better and better over time, all on its own. So here's the key. For a machine, learning really just means pattern recognition. It's all about training an algorithm to spot the patterns automatically. The little things that make all salmon look like salmon and all the things that make them different from sea bass. And you use this stuff every single day, probably without even thinking about it. When your phone unlocks with your fingerprint, that's pattern recognition. When it understands what you say, same thing. When it can read the text in a photo, yep, it is absolutely everywhere. All right, so theory is great and all, but let's see how this actually works in the real world. We're going to circle back to our fish problem and put all these ideas together to see how you'd actually build a system like this. So the goal is crystal clear. We've got a conveyor belt, fish are coming down the line, and a camera is watching. We need our system to look at each one and make a call. Is it a sea bass or is it a salmon? But see, a machine can't just look at a fish like we do. It needs hard data. So we have to decide what specific things it should measure. In machine learning, we call these features. Things like its length, its width, maybe even how bright its scales are. The whole process basically breaks down into a pretty simple three-step workflow. First, you have segmentation. That's where the machine just isolates the fish from the conveyor belt background. Then, feature extraction. It measures all those details we just talked about. And finally, classification. It uses those measurements to make the final call. Salmon or sea bass. Okay, but what happens when it gets it wrong? When it calls a salmon a sea bass? Well, believe it or not, making mistakes is maybe the most important part of this whole thing. That's actually how the system gets smarter. So let's say we start really simple and only use one feature, length. We'd hit a wall pretty fast. I mean, you're going to have some really long sea bass and some kind of short salmon. If you only rely on length, you're going to make a ton of mistakes. It's just not enough information. The real solution is to use multiple features, like length and lightness, and then create something called a decision boundary. Just picture a graph. This boundary is like a line drawn on it. If a fish lands on one side of the line, the system calls it a salmon. If it lands on the other, it's a sea bass. The whole game is about finding the perfect place to draw that line. And here's the really cool part, the learning part. Every single time the system gets one wrong, it takes that information and it just nudges the boundary a little bit. It's trying to reposition that line to avoid making that same mistake again. It is literally actually learning from its screw-ups. Now, you might be thinking, great, let's just add 100 more features. But you gotta be careful. Adding features that aren't relevant, like, the time of day the fish was scanned, that doesn't help. It just adds what we call noise, and that can actually confuse the algorithm and make it perform worse. So all of this training, all this fine-tuning, it's all building toward one single ultimate goal. And this is the real test of any machine learning system. And that goal is generalization. This is the whole point, really. We don't want a system that just memorized the fish we showed it during training. We need a system that can correctly identify a brand new fish it has never seen before. That's when you know it has truly learned something. Now, there are really two main ways a machine can learn. Our fish sorter is what we call supervised learning. We give it data that's already labeled, like an answer key, telling it this is a salmon, this is a sea bass.
But there's also unsupervised learning. That's where you just dump a bunch of data on it and ask it to find any natural groups or clusters on its own, with no labels at all.
What's so cool is that this whole process, it basically follows a repeatable recipe. It's a blueprint you can use to build almost any pattern recognition system, whether you're sorting fish or doing something completely different.
And this is that blueprint, the design cycle. You start by collecting your data. You pick your features, you choose the right model or algorithm. Then comes the training part, and after that, the evaluation. Testing to see how well it actually works. And finally, you have to think about making it all run efficiently. This 6-step loop, it's at the heart of almost all machine learning in the real world.
So if you boil it all the way down, it comes back to this one simple but really powerful idea. It's a loop. You sense the world, you clean up that data, you extract the important patterns, you classify what you see, and then you use those results to refine your model over and over again. And here's the big takeaway, why this really matters. That exact same recipe, the same fundamental logic we used for our silly fish example, is the same logic being used right now to solve some of the most complex problems you can imagine, from finding cancer in medical scans to predicting trends in the stock market.
Which, of course, leaves us with one last, really fascinating question to chew on. We've taught machines to see the patterns that we already know exist. So, what about the invisible patterns, the ones hidden deep in the data all around us? What will they help us see next?